Actually, today my talk is kind of really related to the questions that I just asked, and this also the point that Peter raised. So my talk will be on linearizing the Rasch model, and then so this work is with Mse and Posterior at Cornell. So the Rasch model is a very, very classic model in education data mining, and it has been there for like, I don't know, probably like 50 years by now. And then so the Rasch model is essentially very, very simple. It says that the probability that a student answers a question correctly is simply only a function of two parameters, super simple. One of them is student ability, the other one is question difficulty. And then so this is also known as this is equivalent to the 1PL item response theory model, and it's like very, very effective for modeling graded student responses. It is very simple, but it works. I've seen a lot of works essentially saying that using super complicated models, for example, you can apply all the deep nets in the world and everything, but it doesn't really outperform like the single parameter, two parameter the Rasch model by a lot. So yeah, the thing is, there are many parameter estimation techniques for the Rasch model. For example, you can simply use maximum likelihood, because like the negative log likelihood function under this model is convex. And also you can use Markov chain Monte Carlo, it gives you better accuracy. Or in item response, the context of item response theory, people have come up with things like EM algorithms, whatever. So all of these methods, they essentially, apart from the MC Bayesian methods, they essentially give you kind of an estimate on your of the parameters. And now the question is, what can we provide some kind of an estimate of the error of our estimates? Essentially, can we put some kind of confidence bound around our parameter estimates? So if we recall this theorem, this classical results in signal estimation, which is the Kramer-Rao bound, it essentially says that if you have a likelihood model for your data, and then the estimation accuracy, the error is lower bounded by the quantity related to literature information. So essentially, that's the best that you can do for any estimate. So, so our work in this case, our contribution in this work is to try to introduce some kind of a linearization technique to linearize the Rasch model in order to provide the other half of the story, which is, can we give an upper bound on the estimated error? And so you can think of our contribution as, so a Fisher information based result would give you a lower bound, and our method gives you an upper bound, so the two kind of sandwich. In practice, you can kind of build a sandwich, and then so the real error would be somewhere in between. All right. So in order to derive our method, well, first of all, we'll simply have to view the Rasch model as a special case of probability regression. So imagine we have this matrix of, usually the graded response data comes in a format of a matrix of a bunch of students answering a bunch of questions, but in this case you can simply vectorize it into a single vector. And then also you can design some kind of this, the matrix of regression features D using a simple structure. In this case, it's simply just a bunch of like identity matrices and a bunch of like all ones, and then you can just simply stack them into a huge matrix, and then you can just the third part, which is the student ability and question difficulty parameters, you can just concatenate them and then treat them as like a regression coefficient vector. So in this case, we can cast the Rasch model estimation problem as a regression problem. So let's say there are a total of U number, which is the number of users, and Q is the number of questions. So dimension of the regression problem in this case would be of dimension U plus Q. And then imagine there's no missing data, so the total amount of measurements in our regression model is going to be U times Q. So there are many estimators for this simple classic probability regression problem. So first of all, like the best you can do is, in terms of MSE, which is the mean squared error, if you want to minimize that, then the best you can do is this thing called the posterior mean estimator. But unfortunately, because in our case, for the probability regression, your observed data likelihood model, there's no closed form or any nice form for this posterior distribution once you have multiple observations. So in particular, most likely you'll have to compute this posterior mean estimator using MCMC, like Bayesian methods, and those are extremely computationally extensive. The other thing that you can do is to use some kind of a maximum a posteriori or map estimator. And in this case, the most common approach is to put it like a normal prior on X, your regression coefficients. And this map estimator gives you the point estimate that maximizes the posterior probability. So our approach in this work would be, first of all, realizing that the posterior mean estimator is an estimator that minimizes the MSE among all of these estimators. And our approach would be to develop some kind. Once we realize that, then we can simply develop one kind of a particular estimator. And because the the posterior mean estimator is the estimator that minimizes the MSE, so any estimator that we can analyze and derive and analyze will give you an upper bound on the MSE for the posterior mean estimator. So in this case, we picked to analyze this estimator called the minimum MSE linear estimator, or LMSE estimator, so that we can provide some kind of an upper bound on the mean squared error of our parameter estimates in the Rasch model, and so that we can form together with this Fisher information-based lower bound, we can get some kind of nice two-way bounds on the actual MSE. Right. So and I want to emphasize that our results are actually exact and not asymptotic, because if you recall, like the asymptotic normality property of this maximum likelihood estimators, they are essentially they are only true in the asymptotic regime. So when in practice when you don't have like unlimited data, then it essentially means that these bounds are kind of loose. And but our methods are non-asymptotic; they're exact, and we also have a closed form estimator and closed form expressions for our MSEs. So I'm going to skip all the details and simply give you some kind of a result here. So we make use of two very, very trivial assumptions, or commonly made assumptions. The first one is that our model is the probit model, and then also the second assumption, which is like the student parameters, student ability parameters, and question difficulty parameters, they are normally distributed. So this is like also like a common assumption made in the literature. You can think of, because item response theory essentially says that the student ability parameters come from normal distribution. And also, but the other way to think of it is to think of saying maybe when we don't have any clues on them, when we want to make an estimation, we can simply put like a L2 norm regularizer. So in other words, like these are pretty mild assumptions. So using synthetic data, we can just simulate and test how well our bound works. So essentially, in this case, we kind of see that our bounds are exact. So there's no like asymptotic regime or anything. Just for any size of problem, it actually matches the. And it's also not probabilistic, so it doesn't hold for like a high probability, it is exact. So in this case, we can also use some synthetic data experiments to compare against these different estimators. So why do we want that? So we compare our LMSE estimators with the map estimator, like this maximum posteriori, and also the posterior mean estimator. So on different problem sizes. So in this case, we set up like the regression coefficient vector to be of 5 dimensions, and then we have the number of measurements range from 10 to 200, and then also for a bunch of SNR levels. So essentially, our result says that you can see that the posterior mean estimator always works best because it's MCMC, and then it minimizes the posterior MSE, of course. So, and we see that especially the LMSE method, our linearized method, actually works decently when, first of all, when the problem size is small. So when there's not many data, that linearization actually kind of works. And also, especially for like all of these problem sizes, especially at low SNRs, meaning essentially saying that when the data is kind of noisy, then just forgetting about these complicated nonlinear estimator techniques, but simply resort to the best linear estimator that you can find, it's actually not a bad idea. And more interestingly, we can see that for map estimators, like there's actually like this huge divergence behavior when we go to like super high SNRs. So this is kind of this is a phenomenon that's observed in like 1-bit compressive sensing and 1-bit matrix completion results, that actually for these 1-bit measurements, that the right amount of noise is the best. If you have like almost zero noise, and then that's actually not good in terms of MSE. We also compared our derived linear estimator to these other compared it against these other estimators on a collection of real-world data sets. A lot of them are like simple classic binary regression data sets, and some of them are like educational data sets. And we see that essentially on most of these data sets, we essentially see that there is minimal difference between, in terms of prediction performance, this is AUC. So in terms of prediction performance, there's minimal difference between a linearized version of the model and like these fancy or more, and most likely more computationally intensive nonlinear estimations. In terms of prediction performance, you don't lose much. And also, so now let's see how we can apply our method to the Rasch model in particular. So let's make a couple of simplifying assumptions. So assume that the number of users is equal to the number of questions. So of course we can change that that assumption, but it's not going to give me such a nice form of results, so I'm not showing it. And also I'm essentially assuming that I'm just putting like a simple Gaussian prior on X, which is like there's no correlation between entries. And also, so this result comes after leveraging the specific structure of the Rasch model, because it's, if you parameterize it into like a probability regression problem, there's a lot of redundancy actually. So we're essentially lifting it to like unnecessarily high dimensions. But you can also at the same time leverage the structure to get some kind of a result. And we can actually get like this closed form expression for the MSE, in the exact MSE of our model, as a function of the number of users, of the scale of the problem, and also the SNR, which can be seen, which is actually reflected in the sigma x squared there, right there. Okay, so we also conducted some kind of experiments. So first of all, using synthetic data. So we range over a bunch of problem sizes and a bunch of different SNR levels, and also tested on a real-world data set using which is an algebra test on an Amazon Mechanical Turk, which is a relatively moderate-sized data set. And then using synthetic data, we're able to see that, so the blue line actually says empirical error, which we repeat our setup many times and actually report the average, the MSE of the posterior mean estimator. And then also we report two other kind of bounds, which is the first one, the green one, is the upper bound derived from our method, and the orange one is the Fisher information-based lower bound. We know that in practice, the ideal Fisher information-based bound cannot be achieved because you need to know the ground truth values of these parameters. But in practice, we can simply take the estimated parameters and plug them back in to compute some kind of bound. So we see that these two bounds act like a kind of a sandwich effect. So the real MSE is somewhere in between. And especially we see that for small problem sizes, our bound is actually much closer to the real MSE, the empirical MSE. For very, very small problem sizes, and especially at low SNR, meaning that if the data is noisy, then doing a computationally efficient linear estimator actually doesn't really hurt. And this is a real data example. So here are a bunch of estimates for these studentability and question difficulty parameters, and then we can put these two kinds of error bars around these estimates. So you can see that there is a Fisher formation-based lower bound and also kind of a R method-based upper bound. So essentially, we'll be able to say that it's very likely that the real confidence interval lies somewhere in between these two. So to wrap up, so in this work we have proposed a LMMSE estimator for forward regression, and also we have applied it to the Rasch model. And then so we derive some kind of, so our LMMSE estimator comes with exact and non-asymptotic results on the MSE for the Rasch model in particular. And also, this work is very, very preliminary, so there are a lot of possible directions for future work. So something I can think, among the things that I can think of, first of all, for example, we like to study the relationship between MSE and prediction accuracy, because we are machine learning and data science researchers who care about generalization performance, but not the MSE that much in the end. All right. So that's one thing. The other thing is how we handle missing data. So handling missing data is actually going to change like these closed form results a lot. So it's not going to have this nice form anymore, but we're still looking into that. And also because the Rasch model is a very simple and basic model, so we want to see that whether our this linearization technique can be applied to some more sophisticated models that cannot be simply recast into a regression problem. And that's also worth exploring. So with that in mind, I would like to thank you for listening to my talk, and so now it's the end of the session. Let's actually take these questions offline.